This is the perspective of global vegetation that probably many of you have. It's certainly the one I had for quite a while, because most of my research has been based at this scale. And you've got the productivity in the oceans there, very clearly sort of highlighted with the greens, and the darker greens on land highlighting the forests, and we can see that. And then there's those high productivity areas in the coastal areas, which are very thin strip, and that's sort of the continental shelf scale. And yet the sort of blue carbon vegetation we're talking about is the strip that doesn't even show up on this map. It's these very narrow strip of coastal vegetation around the coasts. Mangroves, salt marshes, seagrasses, and macroalgae, and altogether, these cover less than 1% of the total marine surface. So there is a question: how significant can these actually be on a global scale? And some work's been done to look at that. These are global averages. And you see sort of on the left-hand side there, you've got the burial rate of carbon in tons of carbon per hectare per year. And if you compare the rates you're getting here sort of in salt marshes and mangroves, and seagrasses, they're fairly significant, particularly salt marshes here. And you compare that to the amount of sediment that gets buried in the deep sea, you start to see this is really quite significant. If we calculate that up then on the right-hand side, your right-hand side to the global contribution of these habitats, we can see this is now in teragrams of carbon per year, which is millions of tons of carbon per year. So estuaries are sequestering more than 100 million tons of carbon each year. Salt marshes in a range of 80 million tons, and so on. So we start to see, actually, these might only be less than 1% of the total marine surface area, but they do have a very significant contribution to carbon sequestration. So, and so the total marine burial of carbon from these systems adds up to about 250 million tons of carbon per year. Just again to highlight that, looking at seagrasses, seagrasses have come to the fore quite recently. There was a paper in Nature Geoscience a few weeks ago showing how significant they were. And they have high surface production in their leaves, but also they grow root systems. And these root systems can trap a lot of sediment, not just sediments from the seagrasses themselves, but also the plankton in the overlying water column. As they sink, they get trapped in these root systems. And then there's lower oxygen levels in the sediments, so you get lower respiration of these sediments. You've got high carbon to nitrogen to phosphate ratios. And of course, one key difference in locking up carbon underwater is in terrestrial systems, fire converts organic carbon back to inorganic carbon. There's no fires underwater. This might sound obvious, but so this leads to actually stronger sinks, as Stephen pointed out, than you get in the Amazon rainforest. So John Grace's estimate for the Amazon was about 1 ton of carbon per hectare per year, and Carlos Duarte's for the seagrass beds was 17 tons of carbon per hectare per year. Again, Stephen showed those big peat beds and how that accumulates carbon through time. Seagrasses can do the same thing. So these are 4-meter tall Posidonia oceanica reefs in Spain. They don't just occur in Spain or with that species. They can occur for mixed seagrass beds in Western Australia as well. And so you've got the very small component of the leaves on top and these huge reefs formed from the sediments they trap. So what does this mean for us in Australia? If we're going to take this seriously, is it significant for us? Well, Australia has a very biodiverse coastline. That's not just in the sort of characteristic species we normally see there, but in these coastal vegetation as well. So 39 of the 68 species of mangroves described are found in Australia. Same with 34 of the 60 species of seagrasses, and we have over 1,200 species of macroalgae. These support whole ecosystems with over 600 fish species and about 80% endemism for mollusks and echinoderms. So clearly these are important to our national picture in Australia. In fact, if we look at the contribution in carbon accumulation here. So on the left side, you've got the different habitats: tidal salt marsh, mangrove, seagrass, wetlands, and then compare that to the bottom half of the plot. You've got deserts, croplands, boreal forests, temperate forests, and tropical forests. You can see how significant the marine vegetated habitats are, and when we scale that up by state, we come to a total of about 8.6 megatons. That's millions of tons of carbon per year buried by these just salt marshes, mangroves, and seagrasses. So there's a real challenge to us then to quantify how much carbon can be sequestered by these habitats and how much can be lost through industrial development in these areas. What is the economic cost of this, both in benefits to the economy and in terms of carbon mitigation, as well as to industry in having to address protection of these habitats? And can our current policy frameworks adapt? Because if they can't, we're not going to get anywhere very fast. And the policy pressures are high. Australia is known for its coastal lifestyle. What would Australia be without the beach? So 86% of the population live in the coastal area. That is growing for most of the major cities between 10 and 30% per year, sometimes 40%, per decade. That's just set to increase for the future. And a lot of that is associated with increase in coastal industry as well. There's predicted large increase in shipping over the Great Barrier Reef region of actually 7 to 10% to cope with the current demand for coal extraction in Queensland. We have an offshore oil and gas boom going on in 4 states simultaneously at the moment, which is leading to huge numbers of people arriving to work in Australia and development in these areas. And a lot of them are in pristine areas such as the Northwest Shelf, which have very low coastal populations. And so while people value that as a pristine area, it's also out of sight, out of mind. So there's challenges there. And these infrastructures require large port developments and coastal infrastructures as well, as we can see. So that can take out habitat, and also there's operations like dredging required for these harbours, which disturb sediments. Seabed mining is also becoming a significant topic in Australia. So a number of pressures there that we've got to cope with, and this gives competing trends for those in the policy arena. This map here shows the network of marine protected areas proposed for Australia. And it includes the Great Barrier Reef World Heritage Site, and the pristine Kimberley region's got some parks there. And Australia's also just implemented a carbon tax from the 1st of July, which is in future going to be tied to the European Emissions Trading Scheme. So it's starting to deal in the policy arena with how it tackles carbon and conservation together. But on the other side, the resource economy has all these approvals, and if you look at the maps between the areas where you've got offshore development and you've got marine parks, there's a large degree of overlap. They're going to be subject to the increase in shipping, the port developments, the offshore oil and gas development, and the coastal population increase. So these things have got to be brought together and balanced. The starting point for this has to be quantitative underpinning science. So the policy on balancing these issues is based on really understanding the effectiveness of these habitats in relation to their carbon capture capability, as well as the other policy drivers. So just CSIRO is now funding a program in Australia that brings together a large range of university partners with the CSIRO to measure the amount of carbon that is locked up in these coastal stocks and to address a lot of the uncertainties around their sources and their sink regions, and how much carbon is flowing between these. For example, if you perturb a sediment, how much of that sediment gets lost back to the atmosphere, how much just gets redistributed elsewhere in the coastal zone. We don't know these things. We need to understand these uncertainties. And the effectiveness of these different habitats and species in sequestering carbon. That also requires improved process understanding on the role of community metabolism. So how organisms actually transform the carbon from vegetation as it goes through the sedimentary process, and how that affects the effectiveness of the carbon capture process, and then how that's likely to change in future. And ultimately, we want to integrate this to scale up to national budgets, using modeling and satellite remote sensing to help with that, to characterize uncertainty, and to provide inputs to economic modeling. There are a number of proposed field sites around the coast, and this gives us the advantage that we can contrast systems, for example, temperate and tropical seagrass beds, as well as quantifying those stocks and the fluxes between habitats. So as sediments flow out of an estuary, through a mangrove, through a seagrass bed, we can actually put all that together. So to summarize the approach, we're going to take this field work and remote sensing data and take the carbon cluster research together with existing data sets. And one of the key goals is to get a carbon parameter library to improve our biogeochemical modeling. That biogeochemical modeling will then be used to integrate and provide input to our economic assessment models that are already used quite largely in policy development in Australia. To finish, I just want to come back to this question of the value of coastal carbon. If we look at these, the globally averaged value attributed to these habitats so far, and this is from the IUCN report, Nelman et al. And you can see, for example, mangroves are up to sort of $91,000 per hectare. But, and you compare that to sort of land values, that sounds very high. That is a significant value. And we sort of start to need to appreciate the value of these coastal habitats in dollars. But the problem is, once you put it into dollars, somebody can always pay more. So if I look at the average house price in Perth is 500,000 Australian dollars, about the same as a US dollar. That adds up to about $10 million per hectare. Is the coastal carbon value too low? Are we actually really capturing the true value of these systems? Having said that, the total value of current estimates is already US $25,000 billion per year. And I suggest it could be much more. So to summarize, coastal carbon stocks are significant for CO2 emissions, but they're under threat. In Australia, we're trying to quantify blue carbon, and that requires new measurements and better models. But to value natural stocks requires a much better economic basis. Thank you very much.